All right, so today's class on electrical principles and technologies, we're looking at topic 3. This is resisting the movement of charge. So what is resistance? So this is a property that is going to hinder the motion of electric charge. And it's going to convert that electric energy into other forms of energy. So just some examples here. The resistance of the tungsten wire filament in a light bulb, it's more than 400 times greater than the resistance of a similar copper wire. So when current flows through a high resistance filament in that light bulb, the filament is going to convert much of the energy of the current into light and heat. Now, if that same current flows through a copper wire, the amount of energy converted into heat will be very small so that you hardly notice it. All right, so that was just a comparison of a tungsten wire filament compared to a copper wire filament. So when we are examining electric circuits, we're going to see that voltage, current, and resistance are very closely related. So current is described as the movement of electrons through conductors. Voltage is what makes the electrons move. So that's where the energy is coming from. And then resistance is what is going to oppose the motion of the electrons. All right, so here, just examining again a good conductor and a poor conductor. We've talked about this a little bit already. Copper, it's a metal. It's an example of a good conductor because it allows electric charge to move through it easily, so therefore it has low resistance. A poor conductor, something like plastic or glass, it's going to oppose a movement of charge, so therefore poor conductors, they will have high resistance. So here in this diagram, we're just looking at the negatively charged electrons. They have to force their way through solids. They have to overcome resistance caused by the attraction of positively charged the nuclei and the repulsion of other electrons. So ohm, this is the unit for resistance, and it's symbolized by the Greek letter omega. So this symbol here is the unit for resistance. It's called an ohm. There is a device called an ohm meter. It measures resistance. We talked about a multimeter before. It's a multi-purpose measuring device. It can measure resistance, voltage, and current. So we can calculate resistance. So resistance, again, it affects the current flowing in a circuit. It also affects the potential differences between different points in complex circuits with several loads. So George Ohm, he found that it's possible to calculate the resistance of a circuit or part of a circuit by using the measurement of current and voltage. So last class we had talked about the symbol I. Symbol I represents current. So this is the Ohm's law. So I represents current here. V represents voltage, which is also called potential difference, and then R represents resistance. So resistance is equal to voltage, which is potential difference. It's divided by the current. All right, so that is how we can solve for R. The units of resistance are volts per ampere, right? Because voltage is measured in volts and current is measured in amperes. But volts per ampere is equivalent to ohms. So we're going to be using ohms as the unit for resistance. And we can rearrange the Ohm's law to solve for any of its variables. So if we were looking to calculate voltage, we would rearrange that formula and it would become voltage is equal to IR, so I times R, which is current times resistance. And if we were solving for current, which is our I, it would become voltage divided by R. All right, so those are the three formulas there. All right, so those are the three formulas there. We have the resistance formula, R equals V divided by I. And then we have, if we're solving for voltage, it's V is equal to I times R. And if we're solving for current, we have there I is equal to V divided by R. So let's take a look here at some examples. Oh, here's just, again, those three formulas we just talked about for Ohm's law. So resistance is equal to V divided by I. You can measure it with an ohm meter. Current is V divided by R. You can measure it with an ammeter. And then volts or voltage is I times R. You can measure it with a voltmeter. And here's our units: volts, amperes, and ohms. And then that's the symbols we see in our formulas: V for voltage, I for current, and R for resistance. Okay, so firstly, let's look at the diagram up top here. So here, Ohm's law, from that law that we saw, R is equal to V divided by I. We can see here that we can calculate resistance knowing our current and knowing our voltage measurements. All right, so again, we can use a voltmeter to measure voltage, and we can use an ammeter to measure the current. And once we have those two, we can calculate resistance using R equals V divided by I. So if we have this chart here, and we know R is equal to V divided by I, so our first one here, 1 divided by 1, so R would be equal to 1 divided by 1, which is equal to 1 ohm. That's what we see here. Our next one, our resistance is equal to 10 divided by 10, which is also equal to 1, so 1 ohm. Next one, our voltage is 10, our current is 5, so our resistance is equal to 10 divided by 5, which is equal to 2 ohms. And then last one here, when our voltage is 10 volts and our current is 2 amperes, our resistance is 5. And you can see here are 5 ohms. All right, so that just shows again, if you know the voltage and you know the current, you can solve for resistance. So here's another example. What is the resistance of an electric heater if a current of 12.5 amperes runs through it when it is connected to a 120 volt wall outlet? So you start with what's given. We know our current is 12.5 amperes and we know our voltage is 120 volts. What are we trying to find? We're trying to find the resistance in ohms. We know our formula, R is equal to V divided by I. So 120 volts divided by 12.5 amperes gives us our answer of 9.60 ohms. Okay, so lastly, we would just answer that with a sentence. It's 9.60 ohms of resistance. All right, so just again here, that R is resistance, and it is measured, or the units for it is ohms. V is voltage, and the units for it is volts, and the I is current, and the unit for it is amperes. Okay, so make sure you guys are aware of those three things. All right, so for this example, we know that the stove is connected to a 240 volt outlet, so that is our voltage. The current flowing through the stove is 20 amperes, so that is our current, shown as I in the formula. And what is the resistance? That is what we are trying to find. All right, so we know our known quantities. I is equal to 20 amps and voltage is equal to 240 volts. What we're trying to find is resistance. Make sure you're using the correct formula. R is equal to V divided by I. So 240 divided by 20, which gives us an answer of 12 ohms. All right, so the resistance is equal to 12 ohms. Yes, it's like math. This is the homework. All right, so next here we're looking at resistors. So we will work with these when we do our Gizmos lab. You'll see resistors then as well. So in electronic circuits, resistance is useful for more than just changing the energy of moving charges into heat. It can be used to control current or voltage to suit the specific needs of other electric devices in the circuit. So circuit resistors, they're usually made of a heat-conducting ceramic core, and it's coated with materials such as carbon or metal oxides, metal film, or resistance wire. So this is what they look like, resistors. This is a person taking a lie detector test. It's another application of resistance. It's measuring skin resistance, blood pressure, and respiration. So what happens is when a person is under stress, those things change, and sweat is produced. Sweat is mostly a salt solution. So that's going to contribute to the change in skin resistance. So to measure that change, there's 2 or more metal electrodes that are attached to the skin of the person taking the test. So basically how this would work is if the person is under the most stress, usually they're under the most stress when they're lying in response to a question. So therefore, if they're lying, it's going to increase in conduction between the electrodes, and that's going to show up as a peak on the graph that's plotted by this polygraph machine. Next are variable resistors. So they don't have a fixed resistance. Their resistance will change in response to temperature or light or voltage or any other variable. These are used in a wide variety of electronic devices such as light dimmers, motor speed controls, surge protectors, refrigerator and stove temperature controls. So these are common types of variable resistors. This is a rheostat. They're usually found in like high current electric circuits, like power distribution equipment. This is a thermistor. It's sensitive to changes in temperature. So you'll find these like in thermostats. This one's varistors. These are voltage dependent resistors. They're used usually in a circuit to protect it from high voltage surges. All right, so we'll pause here. So next we're looking at types of circuits. So lamps, TVs, stoves, refrigerators, computers, and many other devices, they operate from the same source of electric energy, but each appliance seems to operate independently of the others. So the circuits are constructed to allow each device to be turned on while the others remain off. How is this done? So this is when we get into looking at the series and parallel circuits. So the first type here is a series circuit. So a series circuit, it only has one pathway. Okay, it's only got the one current path. So therefore, all the moving charges are traveling through each component in the circuit. They're going to go through everything. You can think of a series circuit as a set of parts connected end to end. So if the current is passing through each bulb in turn, it's called a series circuit. There's only one pathway for the current. If this pathway gets interrupted, like if there's a break here or anywhere else, the whole circuit cannot function. And you may have seen this with like Christmas lights and decorative lights. If one bulb stops working, all the bulbs stop working. All right, so another problem, So one problem was the whole circuit can't function if the pathway is interrupted. Another one is that if you add more components, it increases the total resistance of the circuit. So therefore, it's going to decrease the current. So if you add an extra bulb to a series string of lights, it's going to make all the bulbs dimmer. But they do have an important use in household circuits. Switches are wired in series with other components, like wall plugs and lights, and it makes it easier to turn off all the electricity in the circuit. So here this example is again showing a series circuit. There's only one pathway for the current to flow. It has to flow through each of the bulbs and so on. If one of the bulbs stop working, all the bulbs will stop working. The next type is called a parallel circuit. So in this type of circuit, there's several current paths. All right, so here's the battery. The current can flow this way. The current can flow down to here and back. It'll flow this way, and so on. It'll flow all the way across, and so on. So there's several different pathways for the current. The total current is divided with some of the moving charges traveling through each branch or part of the circuit. So it's like a set of branches connected side by side. Okay, so this is what a parallel circuit looks like. Several current paths. We've got 3 different loads here. They're connected in parallel. So these resistors here are connected in parallel. So again, parallel circuits, they have a separate current path for each section of the circuit. So therefore, if there is an interruption or if there is a break in one pathway, it's not going to affect the rest of the pathways in the circuit. All right, because the current can still flow in the other pathways. So therefore, in this example, each bulb here has its own path to the current source. All right, so that's the advantage here. Adding a new pathway with more resistors, it doesn't affect the resistance in any of the other paths. So in a parallel circuit, if you add extra resistors in parallel, it decreases the total resistance of the circuit. So adding more paths for the current to take means it'll have less total resistance. All right, so just a chart here summarizing the differences between series and parallel circuits. In a series, the same amount of current flows through all the components. In a parallel, the current flowing through each component, it'll combine to form the current flow through the source. In a series, they're arranged in a line. In parallel, the components are arranged parallel to each other. When we add resistors in series, the voltage across each resistor is different, even though the current flow is the same. In parallel, the voltage across each of the resistors is the same. In a series, if one component breaks down, the whole circuit will burn out. It won't work. The parallel one, it will continue to function even if one part breaks down because it has its own independent circuit. To calculate total voltage for series, we would add them, V1 plus V2 plus V3. In a parallel, if Vt is the total voltage, then they're all equal. V1 is equal to V2 and equal to V3. Okay, so we'll just watch this video. All right, so next we're just going to talk about house wiring. So practical electric circuits for the home are in parallel circuits. The voltage across each load in a parallel circuit will be the same. So basically, if you turn on one appliance, it's not going to reduce the energy available to the other loads, right? So if you plug in an electric kettle, it's not going to cause the lights on the same circuit to dim. A problem is the current through the wires connected to the source. It increases whenever another branch in the circuit is closed. So when you turn on any appliance in your home, the current in the wires closest to the source will increase. So therefore, the temperature of the conducting wires will increase. It'll rise. So if you turn on too many appliances at the same time, and if the current increases too much, the wires can become hot enough to start a fire. So usually there are fuses put in place and circuit breakers. So those will help against an electrical fire. So those will prevent the fire. Here, so household wiring connects appliances and lights in parallel along each circuit branch. So this is all shown in parallel there. Resistance of a wire also depends on its cross section. So like its thickness. It's called its cross-sectional area or thickness. It's commonly described as AWG, the American wire gauge, and it's a number. So thicker wires, they'll have larger cross-sectional area. So the area will be larger, so they will have lower resistance for a given length. An example, if you have a heavy-duty appliance wiring, so let's say it's a number 12 AWG, it's going to have a large diameter, so therefore it's going to have a lower resistance. It's going to be able to carry higher current without overheating. That is compared to if it was a thinner, light-duty extension cord like a number 16 WG. All right, so power cables. This is an example here, and you can see like it's a thicker wire. So they're made of many thin copper strands. They're going to act together like one large diameter conductor. It's going to reduce the resistance and heating, and it'll also make the cable more flexible. So factors that affect resistance of a wire, it includes the length, the cross-sectional area, the temperature, and the material. All right, so the length of the wire, resistance increases with length. So if you double the length, the resistance will also double. The cross-sectional area, resistance decreases with area. So if the cross-sectional area doubles, the resistance is half as great. Temperature, as temperature of a wire increases, the resistance increases. And then material, so material like copper, and that depends on the structure of the atoms. So some metals will allow electrons to flow more freely than others. All right, and that's where we'll stop today.